This time, I'm going to be talking about debugging and understanding NLP models. Next time on the calendar, it says sequence labeling, but actually I decided that we could leave the sequence labeling for the syntax and information extraction classes. And instead, I'll be talking a little bit about how to design an NLP experiment, which I hope will be useful for coming up with project ideas and things like this. So it will include things like surveys and how to identify interesting research questions and things like that. So this time and next time will be about methodological things that allow you to do better NLP research. So this time is the first of that two-part series on debugging and understanding NLP models. And very often when we are doing NLP research or building systems, we run into a typical problem where we've implemented an NLP system, usually based on neural networks of some kind, because that's what we do nowadays. And you've looked at the code, it basically looks okay, but it has low accuracy or it makes some sort of incomprehensible errors. And if you haven't encountered something like this, then you will soon, so don't worry. It's something that you will encounter very frequently going forward as an NLP researcher. So then the question becomes, what do I do? And a lot of times, when you're first starting out, it's not everybody, but a lot of people basically look at the accuracy, tweak something, go back and look at the accuracy, tweak something else. But it makes it pretty difficult to know what you should be tweaking, right? So the idea of this is to give you a little bit more understanding inside what's going on inside your models, a little bit more understanding of what could be going wrong so you can make model improvements more quickly or fix bugs. So I'm going to talk specifically about 3 dimensions of model understanding, or understanding of the behavior of your experiments that you're running. And specifically, the first one is debugging. And this is identifying problems in your implementation or assumptions. So in other words, kind of debugging things where the underlying model that you implemented is doing something different than you thought, or is doing something different than you thought. A second thing I'm going to talk about is interpretable evaluation. And this is moving beyond the single holistic accuracy metric, like the one that, like classification accuracy or BLEU and machine translation or something like this, to try to dig a little bit deeper. And this can give you an idea of where your model is working well or failing, and can also lead you in the correct direction for making improvements as well. It's also a good source of research ideas. And the final thing is interpreting individual predictions. So this is examining individual predictions to maybe understand why that particular prediction was made. So let's say using something like interpretable evaluation, you've identified some incomprehensible error cases where you don't understand why the model made that mistake. The interpreting predictions, methods to interpret predictions can help you understand a little bit better why that might be happening. Okay, so starting in the first part, I'm going to talk about debugging. And this is something that I cover in this class, or I have covered in this class in the Neural Networks for NLP class for a while. It's something that might not necessarily be covered, but I think it's a really important skill to have. So in particular, in neural network models, debugging is paramount. And the reason why is because models are often complicated and opaque. So they have lots of little moving parts inside them. So it's kind of hard to tell which part is going wrong. Another thing is that everything is a hyperparameter, including your network size, your model variations, your batch size, sampling strategy, your optimizer and your learning rate, even what data you train on. So because of this, it can be hard to tell what's going wrong. And another issue is that you're doing non-convex stochastic optimization. So this is in contrast to something like regular logistic regression of a linear model or support vector machines. And these other models that we traditionally used in machine learning, basically, when you had an optimization problem, it would be a convex optimization problem where you basically ascend a big slope until you hit the top of the slope and get the highest score, or go down the slope until you get the lowest loss function. Maybe down is better. But in neural networks, of course, our loss surface looks a little bit like this. So maybe we start over here and we descend and we get stuck here, or we descend and we get stuck here when actually the ideal place to be would be right here. So because of this, we can't even guarantee that our loss will be, decreasing or converging in any way. So that makes things harder as well. Okay, so there's a number of possible causes that something could be going wrong with your NLP experiment. And I've kind of divided them into a typology here of training time problems, or a typology here. The first part of that typology is training time problems. And the first issue that you might have is that your model is not strong enough to fit your data in the first place. So this could include things like lack of model capacity, inability to train the model properly because you're using the wrong training settings. It could be a bug at training time where you've actually accidentally made a mistake in implementing the model. Another thing is decoding time. I wrote decoding time, but maybe I should write test time bugs. And there could be a disconnect between, okay, typo there as well, a disconnect between training and test. So in other words, the function you implemented at training time is not the function that you are using to generate your outputs at test time. And this is particularly a problem with structured prediction problems like sequence generation or text generation. Another thing could be failure of a search algorithm. So your search algorithm could be failing to find the highest scoring output, which is also a problem. And then once you've ruled out all of the bugs above, you could also have issues with overfitting, where overfitting is, basically we're training well on the training set, but doing poorly on the test set. And another issue can be a mismatch between the function that we're optimizing at training time and the way we're evaluating our models. So basically my suggestion here is if you have a difficult to identify bug, you don't want to be basically optimizing or looking at your evaluation score and then trying to figure out like what's going wrong every time, your test time evaluation score. Because if you do this, it could be any of these many problems and you don't know which one it is. So the idea is you start at the top and work your way down and do kind of controlled tests to figure out whether each of these is actually an issue. So to debug your models at training time, there's a number of ways you can do this. So the first is that you want to be looking at the loss function calculated on the training set. And the reason why is because what training is attempting to do is optimize the loss function on the training set. It's not trying to optimize your accuracy on the evaluation set. It's not trying to generate beautiful looking translations that look good, to your eyes or something like this. It's only attempting to optimize the loss function. So to identify when it's failing to do so, that's what you should be looking at. You can look at things like, is the loss function going down? Also, is it going down basically to 0 if you run training for a long time, 20 or 30 passes over the data? And if not, does it go down to 0 if you use a very small data set? And maybe your model is not strong enough to fit all of your data, but it should be strong enough to fit a very small data set. So there are several potential issues that you could be facing. The first is that your model might not be strong enough. in general, in NLP, one of the big things nowadays is that larger models tend to perform better, especially if you're using some sort of pre-trained model. This is just one example from the T5 paper that I mentioned a couple classes ago, where they basically trained a model and evaluated it on the test set. As I said, you shouldn't be looking at the test set, but also, one kind of interesting thing is that larger models tend to fit your data faster and better, even if you calculate them, with respect to the amount of training time you use. So this is kind of paradoxical because larger models, of course, because they're larger, calculating each mini batch or calculating each evaluation of the model itself takes longer. But nonetheless, what the thing on the left here shows you is that the larger models, this is a 10 to the 9 parameter model, the dark blue is a 10 to the 3 parameter model. We can see that they train in a smaller number of training steps. So despite the fact that each training step takes longer with a larger model, eventually these larger models surpass the smaller models in terms of how well they're doing given the same amount of training time. So this is a very nice paper called The Scaling Laws for Neural Language Models or something like that. So why is this the case? There's an interesting experiment that you can do yourself very easily. Using, and actually it has to do with this non-convex optimization problem. And there's a very simple experiment that you can do where there's a famous function, the XOR function, like this. Where you lay out your data and you have, actually, sorry. That was not the XOR function, that was the opposite of the XOR function. So this is the XOR function. And basically it's like if the two inputs, you have two inputs, and if the two inputs are the same and the two inputs, then you get a negative label. And if the two inputs are different, you get a positive label. And this can be solved with basically a two-node neural network with two hidden states. This is sufficient to solve this problem because basically you can identify whether there's two nodes active or two nodes positive or two inputs positive or two inputs negative. One of the hidden states will be in charge of two inputs positive. One of the hidden states will be in charge of the two inputs negative case. And if either of these are true, then the answer is false. However, if you actually randomly initialize a neural network with only two hidden nodes and try to train it, it will actually fail to learn this function a pretty large amount of the time. And the reason why is because if you have certain initializations, it will converge to a local optimum where it only classifies like one of the two cases. Because, for example, both of the nodes will learn the two-node positive case, or both of the nodes will learn the two-node negative case. However, if you make this size 50, it will learn this almost every time. It will learn this, 99.999999999% of the time. And why? Because each of the individual nodes has a chance of learning kind of this case or this case. And because you have so many of them, chances are one of them is going to learn the thing that you need to know. So this is kind of the reason why a larger neural network, despite the fact that a smaller neural network may be sufficient, can learn more effectively. And there's also a famous paper, the lottery ticket hypothesis, which basically shows that large initialized neural networks have smaller subnetworks that learn the relevant features, and those smaller subnetworks are sufficient, but you only get them if you initialize the larger network, because there's some luck in terms of whether you learn these things. So this is that principle basically taken to the extreme, where a much larger network learns the things that you want to know in fewer examples. So this is a very important concept to have in understanding why large language models work so well. Are there any questions about this? Yeah.
When you say that larger models, they learn better, I mean, if we draw a vertical line at any tokens process, shouldn't we say that all the models are reaching their best potential at the same time? Because they flatten out at the same time.
It's not entirely the case. You see that the smaller models flatten out a little bit faster, although there's also this interesting pattern that at the very beginning, the models don't kind of learn slowly, right? And then after a while, they learn much, much faster. They have this period of very fast learning. So this is kind of where they're, I think they actually have better terminology for this in the actual paper that I've forgotten, but at the very beginning, you're kind of starting to learn useful features whatsoever. And then when you get to this fast thing, you're exploiting the useful features that you've learned to start solving the problem well. And then after you get down to the bottom here, this is where you start learning the edge cases and all of the things that don't appear in every example. If you think of it a different way, this might be the part where you're learning the syntax of English. And then after that, you start learning the edge cases that have to do with semantics or semantic categories or things like this. I don't know if anybody's actually analyzed on a fine-grained level what's being learned when. Or actually, there is a paper on this that I'm forgetting the name of, but you can tell at what parts of training also you learn certain things. I think Ellen of Voita had some work on things. But anyway, long story short, if your model is too small, it's not going to be able to fit your data well. And if your model cannot fit your training data well, it will not do well on your test data, because your training data essentially, not strictly, but essentially lower bounds your accuracy on the test data. Cool. Okay. So another problem that you might have is problems with optimization. Oh, I see. So there's some literature, this is from Zoom, there's some literature that over-parameterizing smooths out the loss landscape. However, I don't know if there's any explanations of the behavior. Yeah, so I do agree. Oh, and I got a request to use a darker whiteboard marker. I will, I'll try to do that, but this is the only black one I have. Yeah, okay, this blue one's darker. So larger over-parameterized models smoothing out the loss landscape is definitely a thing. It's well attested in machine learning, but I actually kind of prefer to explain it intuitively. You can explain it mathematically or you can explain it intuitively. And I think these are both related. Basically, if you have the features that you need to solve the problem already in your model, because they are randomly initialized, essentially, then this would make it easier to find a good optimum, which would result in the loss landscape being smooth. So yeah, I guess you could approach it either mathematically or intuitively like this. Yeah. Yeah. Yeah, so instead of having 50 nodes in one layer, could you have multiple layers? So a very famous result or theoretical result from neural networks is you don't need multiple layers in order to model any function. So single layer neural networks can be universal function approximators. They can model any function that you would like. However, empirically, deep neural networks where you have less width and more depth seem to generalize better in many cases. Not always, but in many cases. Or let me put in the majority of the cases. So I've seen a lot of work where you have the same parameter budget and you can use it either on depth or width, and usually the deeper network works well. Of course, if you only have one node, then that's probably not enough. So there's some limit to that. But I'm not super familiar with the theory of this. So maybe other people in the class would actually have better ideas. But my impression is that a lot of the theoretical, like once you start analyzing deep networks, it actually becomes pretty hard to come up with like solid theoretical results. So a lot of the analysis of neural networks does, like 1 or 2 layer networks. And I don't know if we actually know the reason for this that well. I'm happy to have anybody correct me on this if you know any good results there. Okay, okay. Yeah. Sure. Did they optimize the hyperparameters for each model? I think not, but that's a very good question. Like, did they use a different learning rate for each of these models? Because maybe a different learning rate would have been ideal here. That's a really good question that I didn't check carefully enough, but I think they kept it constant because otherwise it'd be hard to check. Or maybe they did multiple restarts for every model. Yeah, I don't know if they did multiple restarts. I don't know how they'd like average them together and stuff like that. But yeah. Okay, great. So this is an important thing to know. Another thing is that you can have trouble with optimization. Like if increasing your model size doesn't allow you to fit your training data and decrease your training loss very low, almost down to 0. Oh, notably, this is the test loss described here also. So these are not directly evaluating on the training loss. If you evaluated on training loss, I expect that this would be more stark, especially at the beginning of training. Trouble with optimization. So if increasing model size doesn't help, you may have an optimization problem. So you can check your optimizer. For most models now, most people use Atom, and specifically Atom with the kind of like special learning rate schedule that you will also be implementing for assignment 2. But it's basically like you have Atom where you gradually phase in and then it like decreases after that. If you are not using this, if you're not using this in training a transformer model, then you'll probably have an issue. If you're just using standard SGD or if you're using Atom without this special learning rate schedule, it can cause problems. However, if you're re-implementing a previous work, it's very important to look at what they did, because if they're doing something non-standard, there's usually a reason why they did that. They probably chose that on purpose. Yeah. It's for the optimizer, the Atom W optimizer. Yeah. So yeah, if that's not clear in the directions, I'm pretty sure that is part of the assignment. But if not written in this assignment. I might, have made a mistake, so we can clarify that. Cool. Sorry, were there any questions about this, or should I? Okay, I'll continue. So also initialization. So if you're initializing your models differently than other people initialize it, especially if you're not using a pre-trained model, or you're using a pre-trained model, but you have some components that are randomly initialized, you should make sure that you're doing it kind of the same way as previous work. Mini batching. Also, are you using sufficiently large batches during training? So as I talked about before, using larger batches kind of evens out the learning surface and can allow you to have more stable training. So you should make sure that your batch size is large enough, or ideally is as large as previous work that is doing similar things. So in assignment 3, you'll be replicating previous work. Ideally, you'll be able to do that mostly from existing code, or slightly adapt whatever code is existing. But whenever you have to implement new things on your own, make sure that you pay attention to these details, because they're actually quite important. Okay, so that's what I have on training time. The most important thing is that you make sure to see whether you're fitting the data well. Debugging at test time. One major source of problems can be training and test time disconnects. And very often, your loss calculation and prediction functions will be implemented in different functions. This is particularly the case for something like sequence prediction, sequence generation, machine translation, summarization, whatever. An important thing is that this is like software engineering 101, but if you have duplicate code that's doing nearly the same thing, this is a major source of bugs. And another thing is that loss calculation is mini-batched, but very often your generation is not mini-batched if you're generating text. And this can be an issue as well, because in mini-batching, you're doing all of your padding and other things like this. But in your non-mini-batch code, you might not be doing this. So how you can do something like debugging, whether your training and test time losses are different. First, how you can debug mini batching is, if you want to debug mini batched loss calculation, you can calculate loss with a larger batch size, like 32, like what you're using during training. And then you calculate the loss for each sentence individually, or maybe you reduce your batch size to 2 and calculate the same loss. And basically the values of the sum of all of the smaller mini batches and the larger mini batch should be the same, minus numerical precision. If you have an issue here, some suspect places could be things like your padding is off, or your masking is off, or things like this. You can also create a unit test that tests this. So I'm a big fan of unit testing, and basically you can use the Python unit test framework or the PyTest framework or something like this. So every time you make a modification to your code, if you rerun all the unit tests, you can go back and make sure that you didn't break anything. So this is something that I recommend even for research code. If you've never done it before, then there are good tutorials. So another issue is debugging structured generation. So your decoding code should get the same score as your loss function. So if you're doing a generation of an output, you can test by basically calling the function that you use to generate outputs. And the function that you use to generate outputs, like beam search or greedy search or something like this, will almost always be generating the thing with maximum log probability of the output given the input. And in order to do search, of course, you need to keep track of this quantity, right? So you call your decoding function, return the output of the decoding function in your score. And then after that, you call the loss function on the generated output, and you make sure that these match. And if they don't match, you have a problem in your decoding function or your loss function calculation. And you can create a unit test for this as well. So I had a question on Zoom that I will get back to now. I wanted to cover this part first, but basically, your decoding function would be the thing that's doing something like beam search or greedy search or something like this. The loss function calculation would be the thing that calculates your loss for training purposes. So usually these would be in two different functions, like literally 2 different Python functions in the code. Does that clarify? Okay, cool. So another issue is beam search. So beam search, instead of picking one high probability word per time step, like greedy search, you maintain several paths. So you can expand like multiple paths, and then based on the multiple paths, you pick the top scoring ones, you expand the paths, you do this over and over again. So most of the time, what beam search should be doing is it should be improving the log probability of the outputs that you find. And that's the whole point of beam search, right? It gives you a better way to find the highest scoring outputs, like we talked about, several classes ago. So one way that you can make sure that this is, one thing is that this is more complicated than a lot of the other things that you'll be doing in your code often, because you need to step through, you need to maintain a stack of the highest scoring outputs and other things like this. And because of this, it can also be bug prone. You can make mistakes here. So in general, as you make search better, the model score should usually get better almost all of the time. And so if you search with varying beam sizes, you can make sure that you get a better overall model score with larger sizes. And if it's not doing this, then there's probably something wrong with your search code. And you can create a unit test for this as well. Notably, this isn't always the case. Beam search can end up finding, you can make the beam larger and you can find a worse hypothesis. So just to give an example, this is actually one example of this, where if you make the beam size, let's see. No, sorry, this example doesn't work here, but in some cases, basically if the highest scoring thing is in a continuation of the second highest scoring thing here. Okay, sorry. I don't have a good example, and I'm not going to spend lots of time doing that. So just trust me. It won't happen all the time, but you can get a better scoring. You can get a better scoring output with a smaller beam. Okay. So any questions about that? Okay. So a lot of these things had to do with things like sequence generation or other kind of more complicated NLP tasks. The next thing is actually a problem in just about every NLP task, except maybe language modeling, which it's not even clear to me if language modeling is a task. Like an end task that you really care about. So basically every task has this issue. And so the reason why this is an issue is that we will almost always have a loss function, and then we'll have an evaluation metric. And the loss function and the evaluation metric will be different. So it's very common to optimize for maximum likelihood during training. So you try to maximize the log probability of the correct output given the input. However, even though the likelihood is getting better, accuracy can get worse. This is super common. And this is an example from MNIST, which is an image classification data set, but it's like the simplest possible, one of the simplest possible machine learning problems that exists. And it happens even here, so it's going to happen to your problem. So this is the dev loss in accuracy. Ignore training for a second and look at the dev loss in accuracy. And here's the loss. And here's the accuracy here. And what we can see is that the loss very quickly reaches a minimum, and then starts getting worse, but the accuracy continues to get better. A lot of people probably have experienced this. Does anyone have an idea why this happens? Oh, and this loss is negative log likelihood, just for reference. Any ideas? Yeah.
Is it because the model becomes more certain about
Yes, that is exactly the reason why. So just to say it again, it's because the model gets more certain about its predictions. And so basically what happens is we have right answers and we have wrong answers. And the model will slowly learn the characteristics of the right answers. And in general, the accuracy will continue to go up as it starts learning kind of long tail things and things that require a little bit more reasoning about edge cases and stuff like that. But at the same time, the model will become more and more certain about its answers on the training set. As you can see, its loss is going down and down and down and down. But that also means that it gets more and more certain about the outputs on the dev set as well. And that includes being very certain about the outputs where it's wrong. So I don't actually have a slide about this, I realize, but this is a very important concept called calibration. And calibration, basically what it is how well a model's confidence estimates correspond with how likely it is to actually be correct. And this is a very nice paper explaining the idea pretty succinctly and well on calibration of modern neural networks. And what we have here is we have two models. One is LeNet from 1998 and ResNet from 2016. And this model has an error of 44.9. This model has an error of 30.6. So the model on the right is definitely a better model. But if we look at the confidence that the model on the right has, it's very, very confident in its answers, most of the time. So basically, for more than 60% of examples, the model is nearly 100% confident in its answer. However, that's a problem, right? Because it's wrong actually 30% of the time. So the thing on the bottom here, this is something called a reliability diagram. And what is showing is for where the model says it's about 10% certain, what percentage of the time is it actually correct? When it's about 20% certain, what percentage of the time is it actually correct? And the blue bar is, the red bar is if the model basically was correct with about the percentage of the time that it said it was correct. And then the blue bar is how often it actually was correct. So what we can see is that the model on the right, when it says it's nearly 100% correct, it's actually right about 75% of the time. But when it says it's 90% correct, it's actually right less than half of the time. So you can see it's basically far too confident. And the blue bar being beneath the red bar is indicating that. So calibration is a way to measure this confidence. There's something called like expected calibration error. essentially, that allows you to measure the difference between these two things described in this paper pretty succinctly. But going back to this example, the loss here actually is a pretty good metric of how well calibrated your model is also, because you're trying to measure, you're trying to maximize the log probability here, and that's kind of directly correlated. The optimal solution for log probability is directly correlated with essentially a perfectly calibrated model. So given the same accuracy, if you have a perfectly calibrated model, given the same accuracy, a perfectly calibrated model will have better loss than like any other model, essentially. Because of this, your model is getting more and more certain. It's getting a little bit more accurate as it fits the long tail cases, but it's also getting very overconfident. It has too many, has too much confidence in its outputs. So any questions here? Yeah. So if you're doing pre-training, usually pre-training, I guess, is one of the few, like you don't have a downstream task that you would like to fine tune on yet. You're just pre-training the model. Yeah, so if you only see the loss of the pre-training objective, I actually mentioned at the very beginning, language modeling is just about the only task where we don't have this problem. And the reason why is because language modeling is directly optimizing, like the probability of the sentence. And we don't have any other objective that we care about. So, however, for any other task, for text classification, we have accuracy. For machine translation, we have BLEU. For dialogue, we have task completion rate. We have something that's not likelihood that we're optimizing. So if we're not doing language modeling, then this becomes a problem, essentially. You could also consider language modeling as having the accuracy of predicting the next word correct, and then you would in fact have this issue. I saw another hand. Okay, so how do we manage this difference? Oh, sorry, I have a question. In the paper, do they talk about ways to improve calibration of the model on the right? How can we calibrate models? That is a really good question. And this was on Zoom, but how can we improve calibration of models? There's a bunch of different ways to do it. There are some answers in the paper that I talked about. So it's basically, one thing that you can do is you can take the log probability here divide it by a normalization constant and then renormalize with the softmax. And what this does is if this constant is greater than 1, this will make your distribution less peaky. This will make your model less confident in itself. And actually you could also call it tau if you wanted to call it a temperature. And if this tau is less than 1, this will make the distribution more peaky. So it will make the model more confident in itself. This is called Plat Scaling, and it's the simplest way to calibrate models, but it's actually quite effective. So that's one thing to consider first. There's a bunch of other methods. And since you asked, I will also promote my own paper. How can we know when language models know on the calibration of language models for question answering? So this is something where we calibrated language models specifically for the task of question answering. So here, the metric we are interested in is the ability to answer multiple choice questions, not just language modeling performance. So that's the reason why we need to worry about this at all. Okay. So yeah, I will move on to the next part. So there's a bunch of different ways to handle the difference between the loss function and the evaluation metric. We're going to talk about some of these near the end of the class that are particularly useful for structured prediction. But I'm not going to talk about them now because they're rather complicated and not worth doing at the moment. But a very, very easy way you can solve this issue is if you want to maximize your accuracy, you can stop here instead of stopping when your loss is low. So if you want high accuracy, you can stop here with the knowledge that you might get a poorly calibrated model. So if accuracy matters, if you have some other way of measuring the desirability of your model, you just stop when you achieve the maximum desirability of your model on the depth set. Okay, so I'm going to change gears a little bit to something called interpretable evaluation. I think this is a really, really nice tool to have in your toolbox as an NLP practitioner. I've been advocating for this, more of this to all of my, all of the students in my lab, all of the people in my class. So the first thing, this is a rule that, everybody should be following, but people don't follow, maybe as much as they should, which is if you're trying to train models, you should be looking at your data. Don't create a program that doesn't output your predictions, for example. Whenever you are creating a program, you should be trying to output, the predictions and evaluating the predictions that were output, but also so you can look at them. So both bugs and research directions can be found by looking at your input data and also your model outputs. Just to give an example, let's say you have a language generation or machine translation system and your BLEU score is 2 points too low. Instead of getting 24, you're getting 22 and you don't have a good idea why. One very common issue that I've seen multiple times before is somebody had an off by 1 error in indexing their outputs and were accidentally not outputting the first word in the sentence. This is very hard to tell if you just look at BLEU score because your BLEU's a little bit too low. You don't actually have a good idea like why that would be. It's not egregious. It's not so bad that you're like absolutely certain that you have a bug. But if you look at your outputs, you very quickly realize that you don't have a capital letter at the beginning of your word. You don't have a subject at the beginning of your sentence. And then that could lead you to the place where the error happens. The other variety is let's say your model is consistently failing on named entities. Let's say you have a translation model and it's translating pretty well, but it's getting all of the people, places, and things wrong. So that would indicate that, hey, maybe I need to be improving my model of people, places, and things, or my data, or something else like that. So it can both find implementation errors and potential model improvement directions. This is a recipe that I learned when I was working at a large tech company. You can figure out which one if you look at my website. And basically, it's a method for systematic qualitative analysis of model errors. And basically what you can do is, let's say you have a task like text classification where you have like obvious accuracy measures. There you can look at outputs of 100 to 200 examples that have errors in them. If you're doing something like machine translation, you could ask human evaluators to evaluate your outputs and look at the bottom 100 to 200 that have very low evaluation scores or something like this. And then you can try to group them into a typology. This typology can be predefined, or you can do it on the fly. I normally do it on the fly as I'm analyzing errors. So basically, I look at different errors and then I try to group them into common patterns. Just to give an example of a typology, this is a typology from machine translation that you can find in the references for this talk. But basically, they have all errors, which can be separated into missing words, word order, incorrect words, unknown words, punctuation. Then these are all split into finer grained categories. So this is just one example of how you could do all of these. I've actually found that this typology is now outdated. It doesn't match the type of errors, or it doesn't make important distinctions between important types of errors that are present in current machine translation systems, and it too finely distinguishes between like word order on the word level versus the phrase level. You know, you can always remake it on the fly by trying to group errors together. And then once you've done this, if your model is making 80 errors with respect to word sense and 30 errors with respect to the next class, you should be thinking about ways to improve your word sense disambiguation. You shouldn't be thinking about ways to fix a problem that only has 2 instances, probably not yet until you fix the other big problems. Yeah.
So do you do this analysis after like some number of random trials? Like, you do 10 trials, and you just take the intersection of all the examples and you have made a mistake, or like you just do one run and you see whether it's right.
So this is a really good question. So do you do like 10 random trials and find the ones where the models are consistently making mistakes, or do you just like do a single system? Like you can do both, I guess. Interestingly, if you take lots of models, especially if you take lots of different models and take the intersection of their mistakes, you get 2 varieties of things. You get really hard things, which are kind of interesting, and you get annotation errors. So, you know, if there's lots of models making mistakes on them, it might just be an error in your data. But yeah, you could take random trials and find the one with all the random trials as well. Any other questions? Okay, so this is really useful for a task that you really care about. It's good to do for your baseline system, maybe the system that you get in assignment 3 when you reproduce something, to understand where you could improve to make maximal effect. I use this very effectively to improve systems to the point where, you know, like an academic system I made did as well as Google Translate on some language pairs, for example. So it's, I highly recommend it if you want to do well on a task. Other types of analysis you can do are quantitative analysis. And normally, of course, you'll be doing quantitative analysis according to evaluation metrics. But in addition to evaluation metrics, you might want to think about what is the phenomenon you chose to focus on. And is there a way that you can measure that phenomenon in particular instead of just measuring your accuracy or your BLEU score or something like this? So let's say you focused on low frequency words. Is accuracy on low frequency words increasing? Like, let's say we're doing named entity recognition and you were focusing on low frequency entities or something. Is the accuracy on those entities in particular increasing in addition to just the overall F1 scores or something? You focused on a method to better capture syntax. Is syntax or word ordering of your generations getting better, or are you doing better on examples that require long distance dependencies? Or you focused on search, how many search errors are being reduced? So you don't just want to be looking at your BLEU score, you also want to be looking at search errors. And there are some tools to make this easier. Both of these are ones that I've created myself, but I've used them frequently and other people have used as well. So Compare MT is an example of making a toolkit that makes it easier to do quantitative analysis of language generation tasks. And what it does is it calculates aggregate statistics about accuracy of particular types over particular types of words and sentences, and also finds salient examples. So this is an example where I've measured, for machine translation, I've measured the F measure of generating particular types of words bucketed into different instances. And in particular, this is the frequency of the words in the training corpus. And what we can see is the orange system, which happens to be an older neural machine translation system, is very good at getting high frequency words correct, but it's quite poor at getting low frequency words correct. And this is in comparison to a phrase-based MT system. The orange system is also extremely good at shorter sentences, but at very long sentences, it's worse. So what this is pointing you to is, like, let's say you care about the orange system, like the orange system is kind of better overall, so you want to improve it. So maybe you should be thinking about a research direction to improve accuracy on infrequent words or improve accuracy on longer sentences or something like that. I can also just give a very brief demo of this. So what it does is it basically, oops. It basically generates a report like this that breaks down your accuracy according to different like statistics. And so these are kind of holistic measures like blue and length ratio. And then you go down here and get all of these graphs. And actually, you can't see it here because this is kind of from an older version of the system, but you can also click through to examples to find examples of each of these classes as well. Okay. And we also have a more recent version of this for different NLP tasks. And this allows you to summarize different NLP tasks. So it has this kind of analysis for like named entity recognition, part of speech tagging, Chinese word segmentation, et cetera, et cetera. And you can click here on a leaderboard and choose two systems. So we have like the Luke system and the Roberta system, and do analysis between them. And this can tell you things like, okay, maybe this quantity on the y-axis is the difference between the flirt system and the Roberta system. So we can see that the flirt system is like much better at miscellaneous entities, but the Roberta system is, the Luke system is much better on miscellaneous entities, but the flirt Roberta system is a little bit better on people or something, person names or things like that. So this can be pretty useful for finding examples. And there's also like ways to click through to like errors specific to model 1, errors specific to model 2, and things like that. So these are miscellaneous errors that are specific to model 2. These are miscellaneous errors that are specific to model 1. Okay. If you're interested in applying this to your task, tell me. We're trying to make it easier to use. Cool. Any questions about this? Okay. With that, I will move on to the final part. So this is interpretation of predictions and model internals. And so once you have specific examples, sometimes it's relatively clear why the model did poorly there, or at least you can infer it based on your knowledge of how the model works or things like this. But other times you're really not sure why the model would make that mistake in the first place. So for example, you want to know which words were used in making a classification decision to verify its accuracy. So you have a big document and you'd like to know why the model made that prediction so you can verify that it was actually predicting based on the things you think it should be. You want to know whether your model has legitimately learned a difficult pattern or is focused on spurious correlations. So like, let's say you have examples that you think should require, very long distance context in order to resolve. So you want to see whether the model actually was able to pay attention to that context or not. or you want to understand what information a pre-trained model like BERT has captured internally. So there's a lot of different ways that you can do this. And I'm just going to go through several ones that are kind of like the most popular nowadays. So one way that you can do this essentially is by, if you have a model that has made a particular prediction, one thing that you can do is you can perturb individual parts of the model and, perturb individual parts of the input into other things and see how that affects the model prediction. So this is an example of a text classification task between atheism and Christianity from a news group. And this is the post. And then basically, like atheism was predicted with a higher score. But what you do is you go in and perturb individual parts of the input and see how much this changes the model predictions. And once you've done this, the things that change the model prediction the most are the things that you expect the model to be be using in making its predictions. So this is an example of a method called WIME that basically perturbs the model, the inputs into other words. There's also a method called erasure that basically zeroes out the vectors for the input. And both of these can be used to identify essentially words that could be having an effect on the input. One difficulty with all of these methods that I'm going to talk about here is they usually focus on individual words, and there's really not very many good interpretation methods that could, do like multi-word combinations, especially if the multiple words are in different parts of the input. The reason for this is like you could think of like what is the optimal 3-word perturbation that would cause the largest change in the output? But given the kind of like complicated nature of neural networks, it would just be a combinatorial optimization problem of trying to find every single 3-word combination. So it's not possible to solve this exactly, and you need to resort to some other approximate way, and it's not clear exactly what that would be. But anyway, so these perturbation style methods basically change the inputs, see how that changes the output. A more guided way of doing this is basically by doing, by calculating the gradients of the input and having the gradients of the input, like taking the gradient of the input and using it to guide your choice of something that's like an explanation of what changed the output the most. So I am reusing this side. I actually maybe would like to explain it in the context of NLP because that would be a bit more clear for people familiar with this class. But basically what you would do is you would calculate the probability of atheism. You would calculate the log probability of atheism back propagate into all of the word embeddings here. And there's a couple simple techniques in addition to the more complicated techniques that you saw before. But one simple technique is you have the probability of the loss with respect to the embedding of word I. And then you take the norm of this. So it's basically like how much gradient is flowing back into that particular word is an approximation for how important this is. Actually, sorry, I should use the darker marker. So you have the loss with respect to word I. And this is the gradient norm method. And then you can also have the loss with respect to word I multiplied by, or a dot product with the embedding itself. And the idea is basically this is how much the gradient flows back into that particular embedding. This is how much, basically, by another way you can think about this is by having the embedding and not, how much does having this embedding increase or decrease the loss, essentially? So if you zeroed out this embedding, then that would move you in the direction of like turning this embedding into zero. So that would move it in the direction of this gradient with respect to the loss. And so another way you can think about these methods is this method, especially the erasure method, where you zero out the word embedding for that particular word, allows you to tell actually what would happen if you zeroed out that word. This is an approximation that says, well, based on the current point in space, I think if I moved in the direction of zeroing out the word, what would happen? So kind of this is an approximation to like the actual erasure method here. But the advantage is that you don't need to zero out all of the words and see what happens. You can just calculate this once by backpropagating through the entire. Yeah. Oh, what does this mean? So this is the norm. The way you calculate a norm is basically like, yeah. Yeah, so like if it's the L2 norm, it would be like the sum of the squares of the gradients. If it's the L1 norm, it would be the sum of the like absolute values. What does, sorry, what? So it would basically be the gradient of the embedding of the word at this position. So like, you know how you ran the forward algorithm and backward algorithm in assignment 1? It would be the result of the backward algorithm with respect to the embedding in position. Does that make sense? So this is, the second one is the gradient flowing into the embedding times the embedding itself. This is just the norm of the gradient flowing into the embedding. And so like maybe I can give a better example. So let's say this is the embedding. And then the gradient flowing into the embedding is like 0.2 minus 0.2, 0.2. And in another situation, that's exactly the opposite. So this is the gradient 1, and this is gradient 2. And then this is the embedding. This is the embedding itself. So in this case, the norm of all of these would be the same, right? Because you're either squaring or you're taking the absolute values. So like the O1 norm would be 0.6 for both of them. So if you use the first approach, this would say both of these are kind of equally important in making the decision. However, if you multiply the embedding together, you would get 0.6 here, and if you multiply the embedding with this one here, you would get negative 0.6. So I guess maybe a better way to put this is this also kind of tells you the directionality of the effect. So this would say The first one is increasing the probability of this being correct, and the second one is decreasing the probability of this being correct, whereas the gradient norm just tells you this is the size of the effect that the particular like input has on the output. Yeah. Sorry, thank you. I'm glad I wrote that now, and thank you for asking the question. Yeah, in the back. Yeah.
What happens if you have an embedding where almost every value is almost zero? Wouldn't that be like some of the
So if you have an embedding where almost every value is zero, would that become an edge case? Or let's go to the extreme and say, like, we have an embedding where every value is zero. The gradient norm would be positive, or it would certainly be positive. It might be very largely positive. This would always be zero, right? So what that is saying is, right now the embedding, compared to a zero embedding, this embedding is having no positive or negative effect on the output, which is correct, right? Because it is an all zero embedding. Compared to an all zero embedding, it's having no effect because they're the same thing. So basically what this is telling you is, compared to the all zero embedding, how much are you gaining or losing by having this word? In all zero embedded, so like the important thing here is, another way to think of it is from the point of view of erasure. So let's say I zeroed out the embedding of the model. What effect would this have on the output? And erasure is asking exactly that. So let's say I deleted this, from the point of view of the model, I deleted this embedding. If that's the case, then like the all zero embedding would, compared to the all zero embedding, that has no effect. Another interesting thing you could ask, which is actually what Lime is asking here, is if I replace this word with other words, what would be the effect? And so like, then if you had an all zero embedding, then you replaced it with another word that didn't have a zero embedding, then you would still potentially get a positive value here. So that's kind of like the difference between Lime and erasure. Yeah, I saw it. Okay, cool. So another explanation technique is attention. And so attention, basically, everybody knows what it is. We've already talked about it quite a lot. And attention is somewhat interpretable. It allows you to see which values have higher outputs. So you can do like entailment. If you look at entailment tasks or image captioning tasks, document classification tasks, BERT, which we did earlier, in all cases, kind of naturally learned attention seems somewhat indicative of the things that models are paying attention to. So given all of these techniques, however, as I also mentioned during the attention lecture, attention is not necessarily the like do all and end all. It can be completely wrong sometimes, and we have no mathematical proof or mathematical guarantee that it actually will give you the correct answer. So that kind of gives a question like, which one should we actually be using? The answer is, it really depends on what you want to use an explanation for. There's a couple answers to this, which I didn't put on the slides, but I think are worth mentioning. So the answer that this paper gives is they say, if a explanation is useful, it will help human users in learning more about how the model makes predictions. So what you do is you show a human model predictions, and you show them either with explanations or without explanations. And then you give the human a test sample, And you ask the human to simulate the model. You ask the human to make the same predictions as what the model would do. And if the human is able to make the same predictions as the model more accurately given the explanations than they are without the explanations, then that's great. And like you've explained the model more accurately than with the explanations. The problem with this, humans are really bad at simulating models. Like they're just not very good at coming up with it, you know, the same answers that the model makes. So they need lots and lots of training to do it all well on this task. And it's hard to get a statistically significant effect with this in the amount of time that a human's willing to spend on this task. Another problem is all of our explanation methods are not very good right now. So that's another reason why we don't get lots of you know, good results with this task. So to mitigate at least one of those issues, we came up with a protocol that is very similar to the protocol that was talked about before, but instead of having humans do it, we have a student model do it. So basically, we teach a model to be able to predict similarly to another model, and if that model is able to do it in fewer training examples, then we would say that explanations are useful. And we did some experiments, and because now we can do very large scale experiments, we can actually get statistically significant effects. So it's basically an automatic simulation of the simulatability experiment. So still, I think this is a very nascent area. Like we just wrote this paper like 10 months ago, and still, I don't think there's good, you know, ways to determine for sure which explanation method is better. You know, these are only limited to methods that highlight individual words, and there's no easy way to apply them to other types of explanations as well. So, yeah. So anyway, that's basically what I wanted to say today. I have some stuff on probing. Basically, long story short, probing, I've already talked about it in the like, what does BERT learn paper, where I was talking about like BERT learns different things at different levels of its layers. So yeah, we can just leave it at that for this part. But cool. That's about the time that we have. Are there any questions that people have in the end, or shall we finish up? Yeah. Yeah, how do we get the explanations into the student model? There's two answers. One is by supervising the attention. So we add an additional loss supervising the attention of the student model. The other way is through multitask learning, where we train the student model to also predict the explanations in addition to predicting the end task. The latter is better in some ways because it's model independent. You can use it with any student models. Okay, great. Thanks a lot, everyone. We'll finish it with this.